Well, this week's class, the whole week, is dedicated to theoretical physics. This is Theoretical Physics Week. And the first class we're going to be looking at today, Class L, I'm going to take you on a tour. I'm going to take you on a tour of physics and math that you'll learn in different courses and put it all together in an integrated way and show you the landscape. And then the next class that we're going to be doing on Thursday is the beautiful historical derivation of light waves coming from the Maxwell equations. Just amazing. So I hope you enjoy this week of theoretical physics. Chapter L, waves, phasors, and packets. We'll just go with waves. And the first part is the introduction. And before we do this, I'd like to point out the interdisciplinary nature of our course. Look at all the neat applications we've been doing. Atmospheric science, or meteorology, the mirage, the rainbow, astronomy, telescopes, solar spectrum, eclipses, biology, the optics of the human eye, cornea and eye lens, chemistry, light and electron transitions, the hydrogen atom, the sodium, mercury, cadmium, magic, illusions based on optics. Remember the miniaturization at Coney Island in 1922, where we used lenses. Math, we're full of algebra, geometry, trigonometry, and calculus in this course. Engineering, the design of mirrors, the wide angle, the vanity mirror, the makeup mirror, and lenses, camera lenses. Medicine, visual acuity, prescribing eyeglasses for myopia and hyperopia. Photography, f-number, aperture, camera lenses. And physics, the laws of reflection, refraction, spherical mirrors, and lenses. In this chapter, we're going to focus on physics itself. And the analogy I'm making here is that I'm going to take you on a tour. This is not far from my backyard, this beautiful trail, and I'm going to show you along the landscape as we walk along the trail things about physics. And intentionally, I came up with this idea to do this sort of like pulling things together off the top of my head. So that was the idea that we're going to look at. So most of this chapter will be a tour with me as your guide. When I went to school many years ago, my teachers served as my guide. And eventually I learned to see things on my own, and you are encouraged to do the same, and you will do the same as you mature in your study of science and see things that other people don't see. And I like to point out the power of knowing things in more than one way, knowing how to do a problem more than one way. Richard Feynman, the very famous physicist in the United States for many, many decades, he served as an excellent example of a theoretical physicist, working everything out for himself and often discovering new and more powerful ways of doing the math and physics. And he did stress in a talk he gave back in 1964 about understanding things from different perspectives, having different representations of the same thing. And I was fascinated when I heard David Copperfield, the great magician and illusionist, say pretty much the same thing. He says here that the main idea I want to stress here is that he says here, I have 4 or 5 methods for each of the illusions, and I keep changing the methods. That's the key idea here. And he compares himself, this philosophy, with Houdini, who had many ways of escaping from a jail cell. I think there's even a similarity in appearance there. So David Copperfield, the magician, and Forbes said he is the most commercially successful magician in history. And Feynman, Nobel Prize winner in 1965, sharing the Nobel Prize with Tominaga and Schwenker for his marvelous contributions to quantum electrodynamics. So let's begin our tour. And to begin our tour guide, we're going to look at the circle and the sine wave, because I'm going to show you that the sine wave is so important in formulating waves. Now, the circle and the sine wave, this is an application that I developed, but the idea goes back to Newton. So this is well known that the circle is related to the sine wave. Of course, you know, in trigonometry, that's the basic idea, that your y here, when this is your unit circle, your y is going to be the sine of theta. So in this app that Ethan Chester and I developed, Ethan, an interesting story, he's a high school student at the time. He asked Dr. Bennett, the chair of physics, if he could do an intern for free in the summer. So we tried to find something for him. I thought, well, you know, if he knows how to program, I can work with a high school student. And he did. He knew Java. He knew how to program. So we worked on this program, this representation of the circle where the ball, little bead, red bead goes around the circle. And then this is the sine of theta, the y. And here, as the bead goes around, this blue one goes up and down and shakes off this sine wave. And we have a ruler here where you can drag and you can freeze the sine wave and make measurements. And this can become a whole lab. In fact, it is a lab that I use in my physics of Santa music class. So we add another area to our list of interdisciplinary subjects, and that would be computer science, creating a computer visualization for the sine wave. And this is called harmonic motion in physics, and the intimate connection with the sine wave. A marvelous concept that goes back to Newton to relate the circle to the sine wave. Very nice. And then here, this program, when you change the amplitude, you don't change the frequency. But if you change the frequency by making the bead go around, the red one go around faster, then the waves are shorter wavelengths. If you go around slowly, stretched out, which is a nice relationship. And here, these waves always travel at the same speed. So we're basically visualizing the famous formula that the velocity is the wavelength times the frequency. Here's my favorite way to see that formula, where I introduce it to my students in the non-mathematical course, you know, the general education course. If you're on an ideal wave surfing, 10 meters apart, so this is 10 meters apart, the crest, and if 5 go by per second, you know, 5 hertz, so you're here watching, say you're in the water, you're watching, you're going to see here, if 5 of those go by per second, and there are 10 apart, students in my class readily tell me, these are non-science majors, that the speed is 50 meters per second. See? So just, you know, imagine here, put the eyeball here where the crest is. So here, if, you know, 5 wavelengths go by per second and they're 10 meters apart, you can see that's 50 meters per second. So then I tell students that's V, this is F, this is lambda. And now what you did with the 50 meters per second, you got that by taking 10 meters and multiplying by 5 hertz. And look, the units come out, meters per second, meters per second. So then this is V, this is lambda F. And I go home and tell your friends now this formula, and they'll be impressed. So the next section here, L2, is the ubiquitous sine wave. I want to convince you the sine wave is everywhere. Now, when I first learned about the sine wave, it was probably when you learned about it, trigonometry class, and I always felt that the straight line was the easiest, y equals mx plus b. That was the easiest graph to understand. Here's your y-intercept where x is equal to 0. You then have b, your y-intercept, and your slope is your m. So, if you do your, the concept of your rise, here's your rise, and here is your run. If you do rise divided by the run, that's the slope. So I figured that was the easiest function, and this looks scary. Very scary function. Like, what is this, man? This function is scary. So I want to show you that this is actually not very scary. In fact, it's an experiment that I do in my general education class. I have a student at the board on a cart, and 2 students are going to push him, and I tell him to make a natural wave of his motion with the chalk, but look at the class, don't even try to draw anything specific. And when he does that, basically we trace out a sine wave. This is the human oscilloscope, because in an oscilloscope you have an oscillating electrical signal, and then it traces it out, like sweeps it out. And this is a human oscilloscope where these 2 ladies here are serving as pushing for the trace, and you get the picture. Here is one I did with my daughter, and when she did the low frequency, the wavelength was large, and then when she did the high frequency, the wavelength was shorter. So here you have short wavelength, higher frequency, and here is long wavelength and lower frequency, again establishing a representation of this formula, very important formula. And notice, this is the sine wave. It's the way you wave. So if you were to do something, natural, move your pen up and down like this, and then just trace it, just move. Now, it's a little bit hard to do that and move at the same time. That's why we had the 2 ladies push him. You would get this. If you did something irregular, like, up and then down, up, that's a square wave. That's not natural. So the sine wave is natural. Now I would like to show you why the sine wave shows up all over the place. And to do that, we need to review some of your mechanics from your physics class, where you have the potential energy function as mgh, or I'm going to say mgz. And remember, you did things in physics where the kinetic energy plus the potential energy at one point is equal to the kinetic energy plus potential energy at another point. And they said use mgh for near the Earth when you have a ball you're going to drop. And then this is 1/2 mv squared. And this potential, the way it works, the force, if you take the negative derivative with respect to z, you get negative mg, and that would be here the force pulling down. So we're measuring z going up. So here, if you're z above the ground, when you do your derivative with the negative sign, the mg is pointing down. That's your force. And here, if you look at another case, very popular case is to have the spring. So if you have the spring, the mass on the spring with the spring constant K, and here, let's say there's no friction, then they give you the potential energy function. You may remember these from the old days, 1/2 kx squared. And then if you take the derivative minus the derivative with respect to x, you get minus kx. The 2 pops down, cancels, get this, and that's Hooke's law. That if you have a spring at, say, equilibrium, if you pull it a certain delta or certain x, like let's say you measure the x is 0, you measure x as 0 when there's no stretch. Then if you stretch it a certain distance x, then the force is like, wants to bring you back, it's negative. And if you compress it where you push it this way, then the force is opposite again, and then two negatives cancel and the force is to the right. Now let's look at a complicated potential. Here's a potential. This is energy, potential energy, your V function. And here there's a distance, R, it's two atoms in a diatomic molecule. It's chemistry. And this Morse, that's from Morse and Feshbach, physicists, wrote classic book, Morse and Feshbach, the theoretical physics book. And this is Morse, like the Morse potential, named after him. Interesting potential there. And I want to look at something more complicated so that I can show you the power of the sine wave. And here's how we're going to analyze this. Like, we're going to look at some potential energy function that is it could be like crazy, like just like, something like complicated. And what we're going to do is we're going to do a Taylor series expansion. We're going to move, first of all, the axis. We have a situation like this. We want to put the axis here so that you have potential is 0 at the minimum. And this is a stable minimum, or stable extremum, the minimum, because if you have a marble and bring it a little bit to the right, it's going to roll back down, go back and forth. While if you look at something up here, that's unstable, because if you push the marble a little bit, one way or the other, remember the force is the slope, so the force is your slope there, because it's negative, the slope. So basically your force here would be, you could just think of it visually as like you're going to want to slide down. Here your slope is positive, so that means negative the slope, your force is going to want to pull you back. So that's kind of neat. This is unstable, this is stable. So if you do the Taylor series expansion about this point, this is like done in calculus class, your first calculus class, you put the function in, x is 0, and then you take the derivative and put in 0 times x, and then you have 1 over 2 factorial, the second derivative evaluated at 0 point, and that's x squared. And then you have 1 over 3 factorial. And then for these derivatives, rather than putting those slashes, they'll put like a little parentheses 3. And that means take the derivative first and then put in the 0 for the x. And that's x cubed. So for small x, for small oscillations about that bottom point, we can neglect here the x cubed and anything higher, and we just have these 3. But I've chosen this one to be 0, and I can, because potential reference always can pick to be 0. So for the balls falling near the earth, you pick the ground to be 0, but you could have picked the table. That's maybe a meter above the ground. You can pick, you can do whatever you want there, because see, the physics is in the derivative. So the derivative is going to still be the derivative. The slope, you're not going to change the slope by where you put the axis. Then the derivative here, this is the first derivative. See, a derivative is flat there, so this is 0. Well, look what I got. And this is for all potentials. For all potentials, for small oscillations, I have Hooke's law. All right, so this is equal to 1/2 kx squared, like we already looked at. And this is the spring constant. Now, if that's the case, we need to study Hooke's law very carefully. And when we do, we're going to find here, and you probably remember this, that the sine wave is the solution. And if that's the solution for Hooke's law, and I'm going to just go ahead and review that for you, because I think that's cool to see again. F is minus kx, and this is F equals ma, and we can use the notation for the second derivative, dot, dot. Remember, if you have x, your first derivative is your velocity, and your second is your acceleration. So then this says mass times the second derivative, and that's with respect to time, is minus kx. So the second derivative is minus k over mx. What function do you know where you take the derivative twice, you get the same thing back with a minus sign? And the answer is the sine, say sine of omega t. If you take one derivative, you get omega cosine omega t. And if you take the next derivative, you'll get then minus the sine, and the omega pops out again. You get the same thing back to minus sign, so that means omega squared is k over m, and there's your solution. And with the second order differential equation, you have two solutions. So the general solution here, if I write the wave as that function psi, say, I would have some constant here times one of the trigonometric functions and the cosine, because cosines and sines both do this, all right? So we could say A cosine of omega t plus B sine of omega t is your general solution. And then if you want to know what A and B are, they're your initial conditions. For example, if you pull and let go, then B would be 0 because you start off at some position that's away from the center. Like you pull back, you pull over to here, so that when 0 you have A, this is A. Then you let go, it's going to go back and forth like this. And if you wanted to look at the case where you whack it, like if just whack this thing, let's smack it. If I smack it, then it starts off at 0, so that means then the A would be 0, but the B would not be, because I'm starting off and I smack it, then I'm going to get some kind of sine wave. So nice little review there, and that's called harmonic motion, the sine wave, and that all ties together with this arbitrary potential. Now, here's how I solve the differential equation for my students that don't study calculus. I get a spring, and I have a mass here on the end of a spring, and I let it go up and down by, pull it, let go, and it goes up and down. And then with my left hand, I'm following it, and then my right hand following it also, and then I back up. And when I do that, as this is going up and down, and I'm backing up, naturally, I just make the solution on the board. I'm solving the differential equation here. This is a visual representation. Just follow the thing with your hand, both hands, and you have the chalk in the right hand. And I like to use both hands to get in sync. And then I just step backwards, and it's like an oscilloscope. I just trace out the solution. So sine waves, extremely important for everything. And our course is on optics, which is waves, all right? So when we do physical optics, we talk about the waves in optics. So the third thing I want to do is to adapt the sign for waves. Because you see, mathematically, the sine wave is sine of x. This is mathematics. Now, we don't have any really wavelength, period, frequency, all this kind of stuff. We want that for the physics. But here, this is a pure number, so this is dimensionless. And in physics, we want x to be like meters or centimeters. So, and then this is more like, see, radians. See, when you have radians, you have a dimensionless quantity. Remember that if you have, say, here a distance r and an angle theta and a little arc length s, that when you define theta as s over r, you have a radian measure, but this has no units. They cancel out. Meters cancel out. And then if you were to go s, whip the s all the way around, 2 pi r, and then you divide by r, then for the whole circle, say for going around a circle, you would get 2 pi, and that is a pure number. Like that has no feet, has no dimensions, right? Like meters or dimensions could be like feet per second or anything. It's just a number. So to adapt this, before we adapt this, let's study some trigonometry. Notice that if you have x, you go have one cycle is 2 pi. But notice if you have 2x in there instead of just the x, then when x is pi, you got your 2 pi. So in other words, here x is pi, I've already got my, when I double it, I had the sign, I'm going to be here. So I'm going to get 2 waves fit inside the 0 to 2 pi framework. Then if I have 3, then when your x, say here, is 2 pi over 3, then you'll be finished one cycle. So here's 2 pi over 3, and I'm finished one cycle. But then if I go another 2 pi over 3, 4 pi over 3, and then 6 pi over 3 is your 2 pi. So then when I go to my regular 2 pi, I got 1, 2, 3. So when I have sine of nx, this tells me the number of cycles I have. Like how many waves are in there, you might think, say, just like the wave number. Like how many, or the cycle number, how many cycles are there in 2 pi? So that brings us to when we're basically dressing up the sine wave. So in other words, sine of x, we're going to want to use sine of kx. And now if you have x is in meters, then k will be 1 over meters, so that we can then apply the sine wave, because the argument for the sine wave has to be dimensionless. And that will be the way to dress up. We're dressing up the sine wave for physics. And you could also put in an amplitude there, which is important in physics. Like in a sound wave, that's going to relate to the volume, how loud something is, and with light, like how bright, it's going to be related to the brightness. So we get that. Now we need to have traveling motion. So how do we get traveling motion? Well, here's a neat way to see that. Suppose I have a little hump, a little bump. I have y and I have x. And say this function, f of x, is such that if you put in 0, you get bingo, you get a peak. So f of 0 is the peak. And then suppose I want to have the same function down here someplace, which is a distance d away. Well, I'm going to show you that the answer is going to be put x minus d. So let's call this another function, h of x, and I'm going to convince you that this h of x is this function, where we're here instead of there. So f of x, we're here. H of x, we're going to be here. And here's how I'm going to prove it. If I have x is equal to d, then I'm going to have f of d minus d, which is f of 0, but bingo, that's peak. So that means at d, there's the peak. So to shift the function to the right, you just let x go to x minus d. So that is very powerful. And I could then here take my x minus d, and now I have a sine wave shifted to the right. But you probably have seen that in trigonometry. In trigonometry, if you take the cosine, here's the cosine, the green one, and if you were to shift that by pi over 2, then you're putting that minus sign in and you shift it to the right, but then look what happens. That's the red one, that's the sine wave. And you've probably seen that in trigonometry, and that's the complement of the angle x, x minus, well, actually, here's a way to do this. This cosine is an even function, which means you can flip the order of these two. And now, if you take 90 degrees and subtract x, that's the complement. And that's equal to the sine. And you already know that. So this is kind of relating to something we already have learned in trigonometry class, shifting things around. So now all I got to do is let d equal velocity times time, and I'm trucking along. So I hope you enjoy this tour. I'm pulling together from a lot of different sources, like your calculus course here, which your Taylor series. I'm pulling from your physics class here. And now I'm pulling from like your trig class where you did shifting or, shifting sines and cosines around. And that gets us the traveling wave. So in other words, to get a traveling function, all I got to do to this f of x is go x minus d, where the d is vt. So, your function x minus vt is going to be moving to the right, and I can call that function, say, using the sine notation. All right, this is some function moving to the right. And then put a little right there for r, and then if I want to move to the left, I just see the v, I just flip the sign for the v, and this is moving, I'll call that a g. So I have the function moving to the left. So our function here, if I just want to write down the one going to the right, let's say, and it would have the amplitude, here we have a, and we can have sine, and then this would be k. So in other words, what you do here is put in for the d, vt, and then you just have this function here. So now let's study this function a little bit. And to study this, what we're going to do is we're going to let t equals 0 to freeze it. If t is equal to 0 and I freeze it, I have a sine of kx. All right, so here is then the sine, like that. And this is then the function, this function here. This is x. And this here is your amplitude, how tall the wave is. Now notice that the definition of the wavelength in physics is one picture pattern, one cycle. And notice that one cycle for the sine function, you're going to get that when the sine is of 2 pi. That's when you're going to start again. See, so now we're using our math. When the kx is going to be 2 pi, that's when we're going to start again. So that means the k is the 2 pi over lambda. Now this is called the wave number, but we saw earlier that when you have sine of nx, that n is literally the wave number. It tells you how many wavelengths fit into 2 pi. And now you're seeing here, dividing the 2 pi by the wavelength, that you get k, which, this is our k. It's just that in our case, we have a unit that goes with it. It's 1 over meter, all right? So when it hits the x, which is meters, it's going to cancel out and make it dimensionless. All right, we continue our tour. I want to play the game where I look at, say, x equal to 0. I stay put. And I'm going to look at the sine. If we want to look at the sine here of the kVt part, and it doesn't matter if this is plus or minus, it's going to be fine. It's going to be the same result. In fact, you could do plus or minus there. This is going to be a function of t. Okay, so in that case, I'm staying put at x equal to 0. And then I'm seeing like this. It's going up and down at that point, see? It's in time. But if I set this to be 2 pi, one cycle, that in this language of time means the period, capital T. So then I get this neat formula where if I put in now for the k, which is 2 pi over lambda, Vt, then these 2 pi's cancel, and I get lambda is Vt. Well, that makes sense because what that's saying is I have a velocity, and if I let the period, the time for one cycle go by, I map out one wavelength, all right? And another way to see this is that the velocity is the wavelength divided by the period. Your distance is your wavelength, but if your time is your period, that's the time to go one wavelength. That makes sense. Your distance over time, the corresponding time, that's the velocity. if we look at these formulas, we got this key one here, and we now have this key formula, but you know, 1 over the period is the frequency. You can see this very easily. For example, this relationship that's reciprocal, like the period is 1 over f, and f is 1 over t. Like if you do something 10 times a second, how long does it take to do 1? Well, 10th of a second. So in other words, it would be like 1/10 of a second. Notice that the 10 got flipped and the units got flipped. 1 over second became second. So that's how you can really reinforce this formula, that the period is 1 over f and vice versa. So that means this is lambda times f, which is our formula. See, we're getting all the formulas, and this is in the style of theoretical physics where we're like doing everything ourselves. We're not looking anything up, basically. You're just using the most basic things we remember from trigonometry and physics, and we're like putting pieces together. So I want to look at this kVt again, equal to 2 pi, right? And if we were to look at the kV by itself, we have 2 pi over capital T, which is 2 pi f, and this suggests a new definition of an angular frequency. It just 2 pi times f. And when we do that, we have now a lot of nice, beautiful physics. So we have, for example, a wave, and I'm going to take the wave here traveling to the right, sine of kx. Now I can put down c omega t, all right? Because remember, I had this kx, but then if I take the k times the v, that's going to be omega, then that goes up, say that goes here, k times v. And let's just rewrite all the formulas to summarize. We got then the wave number, we got the angular frequency, we got this kv is equal to omega. Probably these are the most important, this one and this one. And the other one would be the velocity, is wavelength time. Yeah, these are the three. These are the big three. So what we're doing here is we're doing our tour. So even though you know this stuff, you may say, why are you doing that? I already had that, I already know this stuff. Well, no, I'm showing you how to bring several courses together, like we're on a trail. And I'm showing you all the features. I know you spent a semester over there, over on this side, doing introductory physics. You spent a semester doing trigonometry. You spent a semester doing calculus. You spent a semester here. But I'm showing you now on the tour, guy. We're looking at everything and pulling it all together. And this is the style of a theoretical physicist, to just pull it all together. So this brings us to L4. Let me go back to mathematics here. Euler's formula. Here's Euler. Now this is an amazing formula. Fantastic. So what we're going to do is we're going to go back to the Taylor series expansion, and we've seen this for the cosine is 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial. Now if you don't remember doing this, I highly recommend you doing this, because back in the class of calculus, you had this formula. N goes from 0 to infinity, and you take the nth derivative of the function, put in 0, divide by n factorial, and have x to the n. It is so easy to derive this because the derivative of the cosine is negative of the sine, the derivative of the sine is the cosine, and you could show this, and I highly recommend you doing this. Take 2 or 3 minutes to do this. Don't look it up. You can do this. This is the starting point, and it's telling you, the first thing is you take no derivative and just put in 0. Well, that's 1, see? So you see, that is very, very powerful for you to go ahead and do that and just write out these terms. And this is the case. I mean, here, if you, this is going to be theta. If you if you take the sine, for example, and you put in 0, you get 0, all right? But then if you take the first derivative, it's cosine, and put in 0, you get 1. And there's the 1. See, there it is. So you can do this probably in 2 minutes, and I highly recommend doing it. It's good practice. Okay, so you got these. Now what we're going to do is now we're introduce the square root of -1, which you already know about. And in engineers, I love the electrical engineers, they use J because they say you can't touch I. I is current, like you don't mess around with I. I has to be current. So they use J. We'll use I here. So I'm going to multiply the sine of theta times I, and I'll have I times theta minus I theta cubed over 3 factorial plus I over here. And then notice that if you cube, well, let me just go ahead and write these down. If you take I and square it, you get -1. If you cube I, you multiply by I again, you get -I. And if you go 4th power on I, multiply by I again, you're going to get 1. See, it's a cycle. So here, what we can do is we can put the I with the theta and cube it, and I cubed is -I. So that's going to be what you get there, -I. And then here, watch this. If I put the I in with the theta and go 5th power, I to the 5th power would just be I again, which is I, see, so that works. And then if we were to do this with the cosine of theta, if you put in I with theta and square it, you get the negative theta squared over 2 factorial. And then here, if I put the I in with the theta and go 4th power or 4 factorial, I 4th power is 1. Amazing. Dot, 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 dot. So if we add these together, cosine plus I sine of theta, we get 1 plus I theta. I'm putting them in order of the powers of theta. Go up here, I theta cubed over 3 factorial. I theta 4, and you get, guess what? This looks like an e to the x thing. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x fourth over 4 factorial. And this one's very easy to do with this formula, because if you put in 0 for x, you get 1. If you take the derivative, you get the same thing back. So then when you put in 0, you get 1 again, and there's your 1 power of x. You take the derivative, you get e to the x again. You get 1. So you're just getting the x to the end over n factorials. So that one, we actually did that one in our head, if you don't need to write that one out. So then you find that here, if x is I, if I put in x is I theta, for here, then I get I theta, I get the I theta squared. So this is the formula. You did the I theta is cosine theta plus I sine of theta. And that Feynman has called our joule. So it's time to look at a joule. I have $50,000 here, $50,000 emerald cut sapphire and pearl shaped diamond halo ring, sold at Blue Mont Nile. Now we come to Euler's identity, which is a fascinating identity. You pick theta to be pi, then e to the I pi is cosine of pi plus I sine of pi. Well, now the sine of pi is 0, and the cosine of pi is -1. So e to the I pi equals -1 plus 0, which is -1. But now if I do e to the I pi plus 1 equals 0, and now I get 5 of the most important numbers in mathematics showing up in an equation once and only once. the ratio of the circumference of a circle to the diameter. The natural, exponential, E. You got I, the square root of minus 1. You got the additive identity, 0, where 0 plus any number is that number. You got the multiplicative identity, 1. 1 times any number is going to be that number, like 1 times 5 is 5. And they're related once. I'm going to call that our opal. Feynman has already named this our jewel, our opal. And here is the opal. And there was a gingerbread contest here at UNCA, and here this one with the math and the physics one won the best gingerbread house. On the roof, the Euler identity appears, and Einstein's E equals mc squared. Marvelous. And a very, very nice gingerbread house with all kinds of decorations and things also. That won the award, 2004. Okay, now in typical theoretical physics fashion, we're going to use Euler and do some trig identities. I remember when I was at the University of Maryland, I was there with a student had gone to Caltech as an undergraduate, and we met up there and both going for a PhD. And he said Feynman was once at the blackboard doing integrals, like from the integral table, just like deriving the integral table, even taking requests from the students. So let me do a couple of these for you. If you take e to the I alpha plus beta, that's e to the I alpha times e to the I beta. And this is going to be cosine alpha plus beta plus I sine of alpha plus beta. That's your Euler formula. And then over here, we're going to have the cosine of alpha plus I sine of alpha. And then we're going to have multiplied by the cosine of beta plus the I sine of beta. And if we multiply this out, we'll have the cosine of alpha times the cosine of beta. And let's do this one next, because that's going to be real. And this is going to be minus the I squared be minus 1. And then there's going to be the one with the I. But the point I want to make here is I already have derived a fairly complicated trig identity in like 30 seconds. And then the sine one will be whatever is multiplying the I. The I keeps things separate, so we're deriving some complicated identities here that you see in trig. And the sine of alpha plus beta, that would be the one that's going to be over here. It's going to be the one that has the I. These two are going to be together. All right, so you could say sine of alpha cosine of beta, and then the other one with the I, plus the cosine of alpha sine beta. All right, amazing. Then if you look at sine, say, of alpha minus beta, that would be sine of alpha cosine of beta. And when you put the minus sign in for the sine, since the sine's an odd function, this is going to change like this. But then if you add these two, look at the cancellation that occurs here, then you're going to get here sine of alpha plus beta, the top one, plus the sine of alpha minus beta, the bottom one. This cancels, you get 2 of these. We're deriving like the trig identity table, table of trig identities, like Feynman was doing those integrals. And then if you let big A is alpha plus beta and big B is alpha minus beta, then you find that if you add these two together, the average is going to be alpha, and beta, if you take the A and subtract the B, divide by 2. And if you do that, then you can look at this one and have the sine of big A plus the sine of big B is 2 times the sine of the average times the cosine of subtract and divide. So like, man, look at this. Wow, complicated identities being developed one after the other. And if you look at this one more, alpha plus beta is cosine of alpha, cosine of beta minus. This is copying from up here, this one here. Then if you let alpha equal beta, you get cosine of 2 theta. It's cosine squared theta minus, the alpha and the betas are the same. And here, this is minus, 1 minus the cosine squared, using cosine squared plus sine squared is 1. So if we use that in here, we're going to replace the sine with 1 minus cosine. So then you get here, it'll be 2 cosine squared thetas minus 1. So we get this famous formula here, and we're deriving all these with the greatest of ease. All right, there's cosine squared theta. And if you want to make the 2 theta, say a phi, like this, then the theta is phi over 2. All right, a lot of good stuff there. Now let's look at L6, the complex plane and phasors. So in the complex plane, what you do is you have x and you have y, and then you have, say, some z is x plus iy. Some folks will label these 1, 2, 3, 4, or some will label them, I, 2i, 3i. That's more of a personal preference. And some just say it's the imaginary to take the I away. But the main thing is whatever's on the vertical and gets an I, and x and y are real. And then what's important here, we'll need to have the length of this vector, and we use the Pythagorean theorem because you have y going up and x, this way in terms of the length of it. So that's going to be the square root of x squared plus y squared. And the way to get this with complex numbers very, very neatly is to define the complex conjugate z star as x minus iy. And then if you hit these together like this, you'll have the sum and you'll have the difference. And that's going to be x squared minus the iy squared. You remember your famous a plus b, a minus b, get a squared minus b squared. And then this is going to be x squared plus y squared. So we want to remember that trick. And the phasor, this is the phasor. So here's a nice little picture of showing the unit circle where you have one. I went ahead and put an I there specifically. And then here, the cosine of theta plus I, sine theta, this is your phasor. You can put a little arrow on there like that. And theta omega times t, and see, it spins around. Electrical engineers love this stuff. They use that so much. Very, very, very powerful. Okay, let's do an example. Let's do a wave example with interference, the famous 2-slit interference problem where this is d, the distance between the 2 slits, say slit 1, slit 2, and then you're going to go off to some screen, that's far away here, and see what's going on. See, if a crest leaves here, then when you look at this optical path difference here, say delta, you don't know what's going to be here. I mean, if this happens to be a crest, then you'll get a reinforcement. 2 crests meet, good news, and you get a bright spot. But if there's a valley here, and if you get higher up, then this angle is going to be a bit different. Then you get dark. So what happens is going to alternate. So this is theta, and this is going to be theta also. This is the right angle in there. So this theta here, you can think of that theta here. Well, just go ahead and blow it up. If we blow this thing up, then if this is theta and this is d, and this is the optical path difference, then if we go here, this angle theta is complementary to there, and that's complementary to there, so that's theta. So let's say here we have a wave, E1, which is some amplitude times sine of omega t. That's going to be what's going to be up here due to this one. Because I'm not changing my x. I'm going to stay where I am and let the time fluctuations go by. So we want this the time component, and say this one, up here, coming from the second one, is going to be some sine of omega t, but there is plus some phase. The delta is the distance, and this is going to be the corresponding angle that goes with that distance. The corresponding angle, that's the phase. And the way we get that is we take the delta and we divide by here lambda. And remember, each of those lambda is going to be worth a 2 pi. When your optical path difference is one wavelength, so it's lambda over lambda, you get 2 pi. So that's the formula. So that's how you get the phi. So the phi is going to be what goes in there. All right. Okay, so let's look at 2 pi over lambda. Whoa. That's k. That's k. And that makes sense. See, that kind of puts everything together. So you can think of, like, if I have kx and I looked at a k times a delta x, like, see, this delta x is like this delta, all right? And that's going to get me the phi angle. Okay, so where do we go from here? Well, what we're going to do is write the sum down as E1 plus E2, and that's going to be E naught sine of omega t plus E naught sine of omega t plus phi. And, I'm just going to leave the phi, leave it as phi. I'm not going to worry about the details. I want the general formula. So here, we're going to say, let's say this is equal to the capital A, and this is equal to capital B, and I use my formula that we saw earlier, the sine. Well, let's go ahead and pull it out, because we already wrote it down. We already have it. We already did this. All right, so if that's the case, then we're going to apply this to get the E. We're going to have, there's a 2. There's an E naught in front of our, signs. So this is the sine of B, and this is going to be the sine of A. So here, the sine of A, that's the one that has the omega t plus phi, and this is the omega t. So that means I'm going to have the sine, I'm going to add them both together, A plus B. So if I add A plus B together, I get A is omega t plus phi, and then B is omega t, and I divide by 2. And then I have the cosine, and the A is omega t plus phi, and I subtract the B, which is the omega t, and divide by 2. These cancel. And that gets me here. This is going to get me 2 omega t over 2 plus the phi over 2. And all right, so I could have here, I'm finished here. I got 2 E naught, which we dropped. And then we're going to have here a cosine of just the phi over 2. And then we're going to have the sine of omega t plus phi over 2. All right, so that's what's going to happen there. But you can see that as the phi goes through different phase changes, you're going to get either going to kill this or not. So here, if I look at, the maximum value for this is going to be just a 1. So I'm interested really in this, the pattern on the screen. So one complication though, and that is, remember when you had V is 1/2 kx squared, and x was your, your sine, your cosines, like for example, A sine, say omega t, you're oscillating back and forth. Your energy is given by the square. So that means the like the brightness or the intensity is in the scientific meter is going to, you have to square the amplitude. So this E is, see this we have to square this thing. So this is like your X. This is like your X, like your solution, but you have to square it when you think about waves. So if you have a wave that's twice as tall, it's going to do 4 times as much damage and knocking you down. 10 times it's going to be higher, it's going to be like 100. So that means here, the intensity is going to go as E squared, and that's going to be 4 E naught squared cosine squared phi over 2. And I really don't care about this thing here because I want the maximum. So I'm really not worried about this thing. So in other words, I is going to be some I maximum, and this is just going to max out at 1. And if your meter is taking an average, all right, there may be another half going, but I don't really care about that. I want to focus on this dependence. I want to isolate this cosine squared of phi over 2. That's where the physics is, right in here. This term, this piece here, that is it. See if I can do this for you to understand like kind of what's going on. Say I have water waves here going in there. Then this is going to start curving. Like, in other words, they're going to spread out, spread out, spread out. And this one's going to spread out, spread out, spread out. And so what I'm trying to show you here is that where they, in the middle, where these two crests overlap and the trough overlaps and the crest overlap, this is going to be a bright spot. This is bright. And then when a crest meets a trough, and a crest meets a trough, you see how we're canceling here. So this is going to be a dark. But then here, you see how they overlap there again. And if you drew the other one in here, you know, it'd be overlapping there. So then you're going to get bright. It's going to alternate. Here's a picture when you have these circles, they're called moire patterns. And you can see here, it's going to, if you do, you know, what I'm doing here is where you have the crest overlapping and the trough overlapping, the crest, you get a bright. This one here is the opposite. Crest meets trough and first, but when they overlap together, that's going to be the brightness, and they alternate. Okay, let's see if we can do the same problem using phasors. All right, so if we want to do phasors, then we have this here becomes phasors. So we have E naught, e to the I omega t, and then plus E naught, e to the I omega t plus phi. Remember, doing things more than one way. So we did it the traditional way, but now we're going to use the phasors. So now if we take this thing and we combine it together, then we're going to get E naught, e to the I omega t factors out, and we're going to have a 1 plus e to the I phi. But what we have to do is we have to like do the square thing. Well, since it's complex, remember the trick, we're going to do like E complex conjugate. So if we do that, we're going to need a little more space. So let's go to another place. All right, e to the I omega t, 1 plus e to the I phi. So we want to have this be multiplied by its complex conjugate. Since the E naught is real, I don't have to worry about that. I just put a minus sign wherever there's an I. 1 plus e to the minus I phi. Okay, so here I get E naught squared, and this is neat. These two, gone. Because if you have E to the plus something times e to the minus something, you get e to the 0, which is 1. That's gone. So I have 1 plus e to the I phi and 1 plus e to the minus I phi. And then multiply that out, I get 1 plus e to the I phi plus e to the minus I phi. And then when these two hit, you get plus 1. So we're getting here 2 times 1 plus, well, let's not do that. All right, so then notice what this is. If you have cosine of phi plus I sine of phi, and you add cosine of phi, and let's see what the minus sign, the phi is. When you have minus phi, cosine's the same. So you get this. You basically have 2 times the cosine of phi. So we might want to just take a pause to look at this. When you have the Euler formula, if you stick the minus sign up there, cosine with the negative is still cosine. Sine with the negative is negative. All right. Then if you add these together and divide by 2, you get the cosine. You get this famous result to relate cosines to exponentials. And then if you were to subtract them, if you take the I minus, if you subtract this bottom one from the top one, the cosines cancel, you get 2 with the sine. So this, divide by the 2i, that's a sine. You've probably seen these before, but this is a good review where we're doing everything from scratch. So this is 1 plus cosine of phi times the E naught squared. And guess what? We know what this is, like we did it. We did it earlier. So this part here we did earlier. If we look at the other sheet, we have the 1 plus cosine of phi over 2 is this. So that means this would be 2 of the cosine squares. So if we have 2 of the cosine squares, this is amazing. That's what we got before. Remember the 4? Remember the E naught squared and the cosine squared? All right. Let's go hunt this down. Here it is. So that was the main, this is the main part. So the intensity was some max, I max, and the cosine squared phi over 2. And I got it again here with the phasors. Very, very powerful stuff. Beats. The phenomena of beats, you have 2 waves where the waves are close in frequency and they have the same amplitude. And then you get the pulsations. Musicians use this to tune instruments. So if we were to add these together, E1 plus E2, we have E naught sine K1x minus omega 1t plus E naught sine K2x minus omega 2t. And then if we remember the formula, if that's an A and this is a B, we then have that formula where we have the sine, you get 2 times the sine of A plus B over 2 cosine A minus B over 2. All right. So that means for the E, we're going to get 2 times the 2. There's the 2. Here's the E naught. And then for the sine, we're going to add these 2 together. So let's go ahead and group the K's together. They're going to add with the X. And then we're going to have the omegas group, and they're subtracted. All right. So we're basically adding these 2 together, taking the average. So you take, there's the average K over, there's the average K times X and the average omega times T. Now the tricky one will be this one where we have to subtract. This was not as easy, but if you subtract, this is going to be K1 minus K2 over 2. And then here, just the omega, it's not that bad. You're just going to have the subtractions going on. And then if you define the average to be K1 plus K2 over 2, and the average omega is omega 1 plus omega 2 over 2. And then the usual definitions for delta, like where you take the difference. Then you get this cool formula. This is 2 E naught, and you get the sine, with the average values. And then a cosine is going to be these delta K's Notice we're not dividing by 2 there, so we have to divide by the 2 here. And this shows a sine wave that's almost the same as the other ones because it's the average, are close together. And this is some modulation going on. And this picture shows it very well, where you have the average, that would be the black one there, and then the cosine, the modulation is going on. So this is called the carrier wave in engineering terminology. And this one here is your modulator, which is modulating the amplitude. See, the amplitude of the wave is changing. So this is like the AM radio does this. All right, that's cool. If you were to look at your definition of your velocity, which was omega over k earlier, if you do the average, they call that the phase velocity. But then if you do, take if it's, in this case you have the deltas, if you do this, they call that the group velocity. And in the book, I show you that for traveling in the vacuum for light, all the velocities are the same. So refer to the book to see that the phase velocity is equal to the group velocity, which is equal to the velocity of the first wave, equal to the velocity of the second wave, and equal to v. Everything's equal, all right? So look at the book. It's just some simple algebra, but it's clever algebra to just show you that all the speeds are the same. See, it's where you get into the case of dispersion. So let's say group velocity and dispersion. See, when you have a medium where the different index of refraction, they travel at the different rates, then the group velocity, this delta omega delta k, this is not going to be a constant. That's not going to be a constant. That's going to vary. See, it's not going to be your like constant speed for all the different wavelengths. You're going to travel at different speeds. So that is important to note. And you could see that if you wrote that down using the formula, say omega is kV, which we looked at earlier, then this would be the derivative with respect to k. You're taking the derivative here of the omega is going to be k times v. So use the product rule. The derivative of the k is a 1, and that's going to be v. But then you have k times the derivative of the velocity with respect to k because it depends on the wavelength. So if we let the index of refraction, which is c over v, and use v is c over n, just to relate this to the previous chapter. So if you relate this to the previous chapter, index of refraction starts to pop in. And then you can write down for the group velocity, you could write down c over n plus k. And now we're looking at a derivative with respect to k, all right, of the c over n. All right, we're just plugging that in. So if we do that, we get c over n plus k. And the derivative here using the chain rule would be minus c over n squared and then dn dk. So here's a cool formula that if you have c over n pulled out, you have 1 minus, there's a k floating around, the c got pulled out, and there's still an n floating around, you get dn dk. Nice relationship there. So the last thing I like to do, and it's more something that was a research project that was done by Dr. Perkins and I was reviewing a paper, and I did this trick where to get the velocity coming back, they had these two speakers, sending something out this way and something out that way. And what I did is I says, all right, I know that this is the wave that we're going to use that's going to go to the right. And the wave that goes to the left from here, I said, well, let's go ahead and shift it 2D. So I have x minus 2D, and I put a plus sign. It's going to the right and going to the left. So I just use the basic principles, and then I add them together. So I want to add this wave coming from this point to the right and this one going to the left. So now when I plug in D for this first one, I get KD minus omega t. That's going to be the first one. When I plug in D for the second one, I get D minus 2D, I get a negative D. But this is bad news, class. Why? Because, you see, the sign is an odd function. So if I pull the minus sign out, so I have minus A sine of KD minus omega t, then these cancel. I get 0, but they shouldn't cancel because they should be reinforced. If the wave, they're in phase, I just shifted this one over and have it go backwards. It should be in phase. It shouldn't get 0. So I wrote to I was reviewing a paper, and then I pointed this out, and then the author says, no, wait a minute, you got something wrong there. And I said, oh no, how did I do that? So that's when Perkins and I got together and we published a paper about this treacherous trap. So here's the trap. Here's why it happens. If you take the sine wave and you shift it and have it go the other way, then notice that a crest is turned into a trough. In other words, there's been a subtle introduction of a phase change. So if you simply take this, move it to the right, and then have it go to the left, then it's the crest that was here. It should be a crest going first, not a trough. See, the cosine doesn't have that problem. If you shift the cosine over, you still have a crest going to the right and a crest going to the left. That's cool. But if you look at the sine, you get into this trouble. So the solution is what they do in quantum mechanics. In quantum mechanics, they don't put the minus sign in front of the t, they put the minus sign in front of the x. If you put the minus sign in front of the x, then everything works out fine. So I just wanted to point that out. You'll get that in quantum mechanics, but for us, we're going to say that when we go to the right and then go to the left, we want to change the sign in front of, in other words, we have e to the I, k x minus omega t, and that's going to the right. We're saying to go to the left, we should put the minus sign in front of the x, like this. So the one going to the left would be minus I times kx plus. So we're saying use this form and this form, and that's what they do in quantum mechanics. In quantum mechanics, they have the e to the I kx and e to the minus I kx. So we're basically finished. If you want the idea of a sum of waves, we can take in general, we can take an integral of the various amplitude contributions for a general wave, kx minus omega t, and integrate over k. So this, more about that later. We have spent enough time on this class. It's time to end.